order, but if you try to do this on different lattices, usually it's to lower orders than that. And another nice thing that on square lattice you will see in a moment, you can differentiate discrete harmonic function, discrete analytic function. Its derivative is again discrete analytic, and then you can differentiate it. So you can, for example, take fifth derivative, and if you prove some estimate for fifth derivative, then you can integrate it back, and you get some very nice Sobolev estimate. So this is no longer true for even reasonable definitions on general graphs. So there are general graphs where discrete analytic functions are defined, but you cannot define, and you can define first derivative, but you cannot differentiate it anymore. So it restricts you the methods which you can use. And also on the square lattice, there are several definitions, so we will work with two which are almost equivalent. So again, okay, let's start with the discrete analytic functions. Well, the correct thing is to say discrete holomorphic, because the word analytic means that function has a power series expansion around every point, and the word holomorphic means that the function has a complex derivative. Now, on a lattice, we cannot really make sense of power series expansions, so we can't use the word analytic, but we can make sense of derivative. We just replace it by discrete derivative. So we can speak about discrete holomorphic functions. In continuous, of course, holomorphic analytic are equivalent. That's sort of one of the main theorems of complex analysis. If your function has one complex derivative, then it has all the complex derivatives. It can be written locally as a power series. So, but somehow the word discrete analytic stuck. So in most of the literature, they are called discrete analytic, and sometimes they are called pre-holomorphic functions. So we will do it on the square lattice, and now we will use, so the following definition is sort of the first thing which comes to mind. So we have, so this is a square lattice. So usually in applications we will multiply it by epsilon. Sometimes we will rotate it by 45 degrees as convenient. And we have a function f which are on the vertices and which is complex valued, is, well, again, is discrete analytic in some domain omega. So let's say I just write omega intersection with this epsilon z squared into c. So we say that f is holomorphic if for every placket, the difference of f along one diagonal is equal to the difference of f along the other diagonal times I. So let me just maybe denote here points as u and v, and well, let's say u, v, w, and z. So in this picture, it would be that f of z minus f of v is equal to I times f of w minus f of u. So if we take difference like this and multiply by I, we obtain difference like that. So basically, that's the equation. So this is that difference, and that is that one. So it's an analog of continuous Cauchy-Riemann equations, which so it's what do the continuous, small remark, what do the continuous Cauchy-Riemann equations say? That derivative of f in the direction I alpha is I times derivative of f in the direction of alpha. And here it's just a discrete version of it. We change derivative for the discrete difference. So can I write here, or it's too low? Yeah. And other letters, yes? Yes. Other letters big enough? Yeah, good. Okay. So one has to check, of course, that it make sort of indeed some parallel definition. So for example, we know that well, okay, we obviously have written an analog of Cauchy-Riemann equation. But for example, is it, one should first ask whether it's enough to write it for every placket. And here just a quick check. So if we have a big domain, say n by n with n square vertices, then our function, it has n square numbers written on vertices. Now, how many equations we would write? We would write for every plaquette an identity, and the number of plaquettes would be the same as the number of vertices, more or less. So we have an n squared identity, which means that if we know our function on the boundary, we should be able to solve a system of linear equation and deduce it inside. So this is sort of a test that it should be not over-determined because we have approximately the needed number n squared, but big enough to sort of work with it. And indeed, it appears that this is the case. So let me just list a few simple properties. So if f is holomorphic, then derivative of f and primitive of f are holomorphic. But they are not defined on the same lattice. They will be defined, well, you can make some definitions on the same lattice, but they won't work as nicely. The nicest definition is on the dual lattice. And it's sort of immediate from this picture, because here we ask that the difference of f in that direction is the same as derivative difference of f on this direction. So if we put this difference in the center of this box, it's sort of a well-defined complex derivatives, because it agrees in two different directions. So derivatives are reasonable to define on the dual lattice at the centers of the squares. So they are both they are holomorphic, but they are holomorphic not if here it's on this epsilon z square, then here it will be on dual lattice epsilon z square, whatever star. So it's just epsilon z square shifted by epsilon over 2 plus I epsilon over 2. So it's just the same lattice, but shifted by epsilon over 2 in two directions. Well, essentially there there is a formula. If I denote this point by p, then the definition is f of f prime defined at p is just what was written there, f of v minus f of w minus f of u, and this is the same as f of z minus f of v. Now there is a sort of a question: what exactly do we want the discrete derivatives to be? Whether we write as discrete derivative the difference or the difference divided by the length, so that it is normalized. So difference divided by the length makes perhaps more sense, because it will converge to derivative when we send mesh of the lattice to 0. So I will divide by the length, and in that way I also take care of this vector being in some different direction. So I will write like this. And then these two things, they agree because of the Cauchy-Riemann equation, because the numerators, they agree up to factor of I, and denominators also agree up to factor of I, so it cancels out. Okay, so this is well defined because there are two things. Now why f prime is discrete holomorphic? Well, so lemma f prime is discrete holomorphic. Well, we have to check that it satisfies Cauchy-Riemann equation in its own right. So let's draw a picture. So we have 3 yellow vertices, and what we want to check is that the difference of f like this multiplied by I is equal to difference of f like that multiplied by I. Now, well, we should use the definition of f only. Well, let me maybe label everything by p, q, Q, R, and S. Let's say what we write. We write f of Q minus f of S. And the question is whether this multiplied by I would give us f of R minus f of P. F prime. And we would just rewrite everything in terms of f. So f prime at Q is the difference of f at those two vertices. So let me maybe just again write. So what was the notation there? U, V, W, whatever, S and T. F prime at Q is f of S minus f of W divided by S minus W. And f prime, S is already there. Okay, so it's S, what are the other letters? P, Q, well, whatever, K. And f prime of S is this difference, so it's f of U minus f of T divided by U minus T. And the question mark asks whether it's equal to f prime of R, where we can write it as this difference. So f of T minus f of K divided by T minus K minus, here I also forgot minus, and f prime of P is W minus U divided by W minus U. And, essentially, what we have here is that we have f of K, W, U, and T with some coefficients on the left and also on the right. And essentially, if the lemma is correct, this identity has to be to hold because values of discrete analytic functions, these 3 points are independent. There is no relation between them whatsoever. If I come up with 4 values here and I put another value here, I always can add 4 values at the corner, so that's a discrete analytic. So it has to be an identity, or otherwise, well, the course will be cancelled. And actually, I never checked. No, what do you mean it's not the same? I think it's the same. Well, the definition above, so I'm checking, so this is what is changed. So this is the Cauchy-Riemann for f prime. It's this. Wait a second. So R minus P is Q minus S. No, because I just saying that the vector. No, it's like that. That when you rotate by I, you also multiply by I. No, I think it's correct that if you take no, it is correct. So the derivative in this direction is I times derivative in that because the direction is such. Yeah, no, I think it's actually identical. I thought that I pictured rotation of something by 90 degrees. No, but I think the pictures are identical. Well, no, it's sort of, well, we have to check that I over K minus W f of K here, well, minus something. So let's check what is the, well, minus 1 over T minus K f of K. So let's check just these two coefficients. So I have to check that, well, whatever, that I times T minus K is I times T minus K is equal to minus K minus W. So T minus K, what was T minus K? T minus K is this vector, and K minus W is that vector. And what I write here, that if T minus K is multiplied by I get minus the vector K minus W, and that's correct. So if T minus K is multiplied by I, it just rotates counterclockwise, and you get exactly vector from K to W, but in the opposite direction. So it agrees for this coefficient, and it must agree for the other coefficients by rotational symmetry. So there are points somehow not different from each other. Okay. Now, how do we define the primitive of f? Well, the primitive of f is defined the same way. So well, the opposite of this way. So let me just erase this picture. Not the picture, but perhaps this formal way. So so primitive of f, of course, is defined up to additive constant. So we have to fix value somewhere. And it's uniquely defined in simply connected domains. So what we say, let's say that, okay, so what was this z point? So for example, we set primitive, well, okay, so set primitive of f equal to g, where g of q minus g of s is equal to q minus s times the value of f here. So we define the difference of g for any neighboring neighboring pair of the yellow vertices. Lemma is that it is well defined on the dual lattice. Well, if we are in simply connected domains. Now there is also, maybe I want, because you might ask, I want to make an immediate remark that with this, so this is the most straightforward definition, but it will actually give it. So there are, if let me just plot the yellow lattice. So this definition actually will give, if we start like that, it will start at q and s, then we would also get it at this point, at this point, at this point, at this point. So we'll somehow get it not at every point, but at each other point on the yellow lattice. And similarly, if we start with r, we get it on each other point on the yellow lattice. So we somehow yellow lattice splits in two, and there is primitive of one on one of them, primitive on another of them, and you can take a priori different constants. So we'll do later a bit different definition which connects them. But this is actually also manifestation of a certain property of this equation, which is that if you look at this equation, then, well, it's a complex identity. So we can write it as two real identities, that real parts of these two things agree and complex and imaginary parts agree. And then real part of this would be equal to real part of the right-hand side, which is just the imaginary part of this bracket. And vice versa, imaginary part of this will be equal to real part of this bracket. So a small remark is that if we take our original lattice and if we cover it into two colors, then our Cauchy-Riemann equation, it connects real part on black vertices with imaginary part on white vertices, and vice versa. So in some literature, because of that, people say that there are like two half functions, two demi-functions, and one has real part living on white vertices and imaginary part on black, and the other way around. And a priori, unless we introduce some boundary conditions, they are not connected. So, for example, if we pass to scaling limit, they might converge to two different analytic functions, unless we somehow couple these two halves in some way. So the remark is that usually what is done is that people just say we only deal with real part on black vertices and y part and imaginary part on white vertices, and quite often, so for example in Rick Kenyon's work where he observes them in dimers, this arises naturally, that his dimer function is automatically real on black vertices and imaginary on white, and it's analytic. But if we want to consider some complex number, we have somehow to relate them, otherwise we might end up with two unrelated analytic functions, and we will see that we'll have a slightly different definition later which actually relates them in some way. But this is a small remark, maybe I should have made it immediately. And it also, well, it is also here that the most logical definition of primitive, it somehow is different for two different lattices. So there you have two different additive constants. It's because one has real additive constant, another imaginary additive constant. So it's maybe a bit unnatural, but with the other definition it will work better. Okay, now well, why it is well defined? So we have this thing, this yellow lattice, and what we did, we specified for our function difference along each of those diagonal edges. So what do we have to do to check that our function is well defined? We have to check that when we walk around a placket in this lattice, the differences, they sum up to 0, that we don't have any periods, that if we divide it here and then we add something to define here, add something define here, add something to define here, and when we come full circle, we added 0. So as we don't get a contradiction. And if we check it for every placket, it will work for any simply connected domain without holes. And for domain with holes, what might happen that when we walk around the hole, we add some period. So it's like for the usual analytic functions, if domain is simply connected, the primitive is well defined. If you are in an annus, then the primitive might have a period around the hole. So we have to check, we have just to check that the differences, they add up to 0. So we have to check, well, let me again write what is here, let's say, S and Q and, well, whatever, A and B. So we have to write that G of Q minus G of S plus G of A minus G of Q plus G of B minus G of A plus G of S minus G of B. We have to check that this sums up to 0. And each of them is given by a value of f somewhere. So it's z, t, these points. So there is a point, what is it here, z. There is a point here which we denoted by k. There is a point here which we denoted by t. And there is a point there which we denote, let's say, by ABC. So GA minus GQ, it's, what is it? It's A minus Q, F of K. And G of B minus G of A is F of C times B minus A, plus B minus A times F of C. Plus G of S minus G of B is F of T times S minus B times F of T. And now I forgot G of Q minus G of S. So it's F of Z times Q minus S. And the coefficients we have, so we have a sum of F around the placket, which should be 0. And this is exactly the condition we have here that the sum of f around the bracket with some coefficients is 0. And the question is whether coefficients are the same. Well, the coefficients, we can divide them by the length of the lattice, of this yellow lattice mesh. So they all have value 1. And if we divide so let's maybe divide so that the coefficient at z is equal to 1. If we divide so that by q minus s, then we get 1 here. Here we get a minus q, and we divide by q minus s, and we'll get coefficient I. So it's what happens if you divide this vector by that vector. So their ratio is I. Here you would get minus 1, and here you would get minus I. So the coefficient when you go around the bracket, they are just 1, I squared, I cubed, I to the power 4, which is again 1, and so on. And they are also such in this identity there. If you go around the bracket, the coefficients will always be multiplied by 1. So in this identity, if we move it all to one side, then the coefficients will be at z. The coefficient is, what is it, 1, and then at c, no, it's not, well, okay, so at z it is equal to 1. Then at u it is equal to minus I minus, so it's equal to I. Here it's I squared, here it's minus I. So everything agrees. Yeah. By the way, if you get not multiplication by I but by minus I, then what you get end up with are anti-analytic functions. So it makes no difference. Okay, so this is the primitive of the function, and again it exists by these Cauchy-Riemann equations. So can I erase this? Yeah. Okay. Now more properties. So as we mentioned, there are two half lattices. So the other property that if we restrict f to two half lattices, let me just denote f white and f black. So they are harmonic, discrete harmonic on those lattices. Well, let's say epsilon z squared black, epsilon z squared white. So these functions, which are real and imaginary parts, they will be discrete harmonic like they are supposed to be, and like they are in the usual case. So let me draw a picture again. So it's okay. So what do I have to check? I have to check that, this is Z, W, T, let's say U and V, and have we ever denoted the other points by something? Well, whatever. Let's say K, L, M, A. We want to check that f Laplacian. What will be the Laplacian on this black lattice of f at point z? Well, it's the sum of neighbors minus 4 times the value at z. So this is the sum of neighbors. So it's let's say sum of f of x minus f of z, where x is the neighbor of z. And there are 4 neighbors in this case, so it's f of m minus f of z plus f of l minus, let's say, f of a minus f of z plus f of v minus f of z plus f of l minus f of z. So basically, it's the sum of 4 differences along the vectors emanating from z. And now what does the Cauchy-Riemann equation say? It says that this difference is equal up to factor of minus I to the yellow difference. So each of these differences we can rewrite as a yellow difference along a vector rotated by I. So the sum of these 4 white differences is minus I times the sum of 4 yellow differences. So it's equal to minus I. So here we use Cauchy-Riemann equations. It's equal to minus I, and m minus z gives us t minus k. F of t minus f of k. And then the next one gives us f of u minus f of t, and so on and so on and so on. And since the yellow differences, they go around, then what we do, we just cancel everything out, and we get 0. Yes? Well, if it's complex, then it's a complex harmonic function. Harmonic function, well, yeah. So as I said, we can do 2 things. Either we say that f is real on black vertices and f is imaginary on white vertices, and then there are 2 real harmonic functions. One is better than to define by I, so it's not imaginary harmonic but real harmonic. If both of them are complex, still this identity holds, and it means that f black is a complex harmonic function. So it's a complex function whose Laplacian is 0. But it just means separately that Laplacian of real part is 0 and Laplacian of imaginary part is 0. So for us, usually, as I said, for us, usually there will be no problem. We work with slightly different definition, which connects the 2 halves of a function, so they will be coupled together, so they will converge to the same thing. But and also there are other definitions of analytic functions where they're sort of thematically coupled. So it's just a priori a problem which might exist. Okay. Now, well, let's maybe formulate a theorem, well, no, maybe another property. Let's just continue with properties. So yes. Yes. Well, I don't know. So maybe what I suggest, I can, in the last lecture, give sort of a list of definitions people tried and comment on them. So I mean, first, what I say that this is not a problem. This is not a problem. Problem is different. Problem is that you can't multiply such functions. But on triangular lattice, I mean, what do you do on triangular lattice? Well, let's. So where do we define function? On vertices or on edges or vertices? Okay. So what kind of equations do we ask for? Suggestions. Hexagons. So here, if you ask one equation per triangle, then you get way too many equations because the number of triangles is twice the number of vertices. So it turns out that, so actually, you're right. So Novikov has written a series of papers where he insists that one should do discrete complex analysis on triangular lattice. So there are a few papers with Dinnikov, his former student, and a few papers of him alone. But well, I can't really say that there is some big, well, that philosophically it's better than square lattice. At least the arguments he brings, they are well, they're not convincing. They are just, this is as good as definition as on the usual lattice. And I haven't seen it applied probabilistically yet. I haven't seen a model where this relation arises. So his relation is, since you have twice as many triangles, you just ask for relation for each other triangle. And his relation is that, so our relation was that when around a square you walk, sum of f at the vertices of the square multiplied by 1 I squared I cubed, sum to 0. So when we walk around the triangle, you should take cube root of unity. So let's denote it by, well, so it's multiplied by 1 cube root of unity and another cube root of unity. These three values sum up to 0. And you can check that it's discrete approximation of Cauchy-Riemann equation. You can also check that it's sort of equivalent to what Kirchhoff would suggest if we look at this as medial lattice of something. So this is another relation. So there are many relations, and maybe essentially, so why we are doing it for square lattice, because simple properties like the one I said here, they work very well on all reasonable lattices. So here also, if you properly define a primitive and derivative, you can easily check their properties. So all the linear analysis up to Riemann-Roch theorem works very, very well. Now the nonlinear things, they are problematic. So it's okay. So okay. So the next property. So if so there was this property, there is this property. There is another property. Maybe I'll cut it in, that this Cauchy-Riemann definition is equivalent to the Kirchhoff definition. So Kirchhoff definition, if you remember, it was when you put function on edges as a flow, and you ask that the flow around any placket is 0 and flow out of a point is 0. So we have to change our definition to put it on some edges to have a flow of liquid. So one way to do it, for example, so let me draw again a piece of a square lattice. Actually, there is one reason why we do it on square lattice. It's much easier to draw than triangular lattice. And hexagonal lattice is even worse because it's not composed of the straight lines. So it's okay. So what we do, let me just use another color, maybe. Yeah, maybe that's a bit better to leave it as an exercise. So for example, we can draw this lattice. So we take f, which is holomorphic on the white lattice, and then we define, well, let's say another function, whatever, g, which is Kirchhoff holomorphic on that lattice. And how do we define it? So if I want to define it for this h, suppose that the h is bounded by vertices x and y. So what I put g of the vector from x to y to be equal to, let's say, y minus x times f at the center of this h. So so this is the center of this h there where f lives. So on every edge, center of the edge, there is a vertex of the white lattice. So white lattice is medial for this orange lattice. And what we do, we just put this number on this edge, but we want to put it on oriented edge. So to do so, we put it multiplying by direction of the edge in one direction or direction the edge in the other direction. So it then becomes antisymmetric. So you can check two Kirchhoff conditions. So what were the two Kirchhoff conditions? Well, let's leave this as an exercise. Exercise, check two Kirchhoff laws. And well, the Kirchhoff law, one Kirchhoff law, it says that the flow around the orange placket is 0, and flow around this orange placket can be written in terms of values of f around this black-white placket. So you get to use its Cauchy-Riemann relation. Now, if we want to do the first Kirchhoff law, if we want to do Kirchhoff law for this point to check that the sum for edges semi-identical from this point is 0, then we get to use values of f around another placket. So you see there are two types of plackets, and the black plackets, they will give second Kirchhoff law for faces, and the white plackets, they will give first Kirchhoff law for other points. So it's again sort of manifestation of this thing that we have half of the lattice responsible for real part and half of the lattice responsible for the complex part, for the imaginary part. Okay. So the exercise is to check that you indeed have two Kirchhoff laws, and it works vice versa. If you can do this definition the other way around. If I have a flow G, I can define f in that way, and I can check that f will be analytic if G satisfies two Kirchhoff laws. So it's kind of back and forth. There is no difference. So maybe I leave it as another exercise. So the exercise is indeed that the two things are equivalent. Okay. Now another property is an analog of Moreira theorem. So Moreira theorem gives yet another definition of an analytic function. It says that function is analytic if and only if its contour integrals are 0. It's somehow different from the usual definition, like homomorphic analytic regular, that it's not an infinitesimal, not a local definition, which says derivative is 0 or something, but it's global definition. You work with some global objects. And for us, it's nice because when we pass to scaling limit, it's much easier to control integral of a function along an interval than derivative of a function. Because if function, say, converges in sup norm, you can control integrals of it. But you cannot control derivatives without doing some extra work. So for us, it's nice. And Moreira's theorem says that f is homomorphic if and only if for every contour gamma, contour integral along gamma of f is equal to 0. So dz. So we essentially proved this theorem already because what did we prove? We proved that f has a primitive. So primitive is a contour integral around contour from a to z, where a is some fixed point. In proving that there is a primitive, in particular, we prove that if contour is closed, the contour integral is 0. So we prove if there is a contour which goes from a and returns to a, then the contour integral is 0. So it means that if f is homomorphic for closed contours, then, yeah, maybe I should write any closed contour. Let's say any closed contour gamma, the contour integral is 0. Now we have to check the opposite, that if for every closed contour gamma the contour integral is 0, f is discrete homomorphic. And now in the continuous one has really to check this. Here one does not, because our Cauchy-Riemann equation, it just says that for a 1-by-1 contour, integral is 0. So indeed, the Cauchy-Riemann equation, what does the Cauchy-Riemann equation say? Cauchy-Riemann equation say, as we discussed, that if you sum around the square, around the corners of the square with coefficients 1, I, minus 1, minus I, then everything is fine. But this sum is exactly contour integral along this simplest of possible contours, because we integrate times dz, and dz is exactly changes if dz is 1 in this direction, it's I in that direction, it's I squared and minus and I cubed, so it's exactly that. So here it's trivial, the equivalence. Okay. Yes, the contours live on the dual lattice, yeah. Well, it's even more. You see, I somehow have chosen the contours to live on half of the dual lattice. So it's you can make definition where they would live on the dual lattice. We'll probably be doing it tomorrow, but it's yeah. Okay. So let's do one more property. suppose that we have f. So now in this property, I will have continuous function. So I will just add epsilon. So suppose that f epsilon is holomorphic on this epsilon z square lattice. And suppose that f epsilon converges to some f small inside domain omega. So what do I mean by that? I mean that we take domain omega, we put mesh epsilon lattice on it, and we assume that on mesh epsilon lattice there is a function f epsilon which is defined there. And as mesh of the lattice goes to 0, it converges to function f. So that can be understood in the, say, well, you take f epsilon defined on the lattice, you continue it linearly into the plackets in some way, and then it converges everywhere. So I want, I mean, when we will be applying this, that will be more or less the setup. So the conclusion is that then the function f small is continuous holomorphic function. So if there is a limit of discrete holomorphic functions, it has to be continuous holomorphic. Yes? Sorry? It converges uniformly, yeah. So it's, yeah, double error means uniform convergence. No, it's more just to save time that I didn't want to specify what is convergence in some norm or something. So here, for simplicity, we assume that it's just convergence in L infinity norm, that the difference tends to 0. That's it. For some, it will work for any reasonable kind of convergence, what we are going to do. OK. Well, the proof is very easy. What we do, we take any contour. So we take like any reasonable contour. And the discrete contour integral of f epsilon is 0. So what it is very easy to obtain that if I take well, if I take discrete contour integral, so let me just put epsilon here, or rather contour sum. Well, okay. So suppose yeah. So the contour integral around contour gamma epsilon of f epsilon is equal to 0. So if gamma epsilon is some contour on the discrete lattice. So now choose gamma epsilon to approximate some contour gamma. Now what will happen is that as epsilon goes to 0, this will converge to the integral around gamma of function f. Why? Because if functions converge in L infinity norm, their integrals converge. So Riemann sums converge to Riemann integrals. And since those were 0, the contour integral of f small will be 0. So the conclusion is that contour integral of f small for any contour gamma is equal to 0. So the conclusion is that f is holomorphic. Now, to be able to approximate by discrete, we better take contours which go in the direction of the lattice. So we easily get this for all the, say, square-shaped contours. And for Moreira theorem, it's enough. It's enough to take any dense family of contours. So squares would be enough. So this is easy, but we assumed already that there is convergence. If we don't assume that, if we want to prove that there is convergence, if we just have a sequence of discrete analytic functions and we want to prove that it converges to something, we have to do some estimates. But once it converges to something, it's clear that what it converges to is discrete, is continuous holomorphic. Okay. Now, to that effect, I will state one estimate, and maybe I don't know. Should I prove it today? Yeah, maybe for now. Maybe I will leave it for the practice session. So this is an equivalent of Harnack's inequality. So in this setting, it was proved by Verblunsky, and yeah, maybe I should say, yeah, okay, I will say about history a bit later. So Harnack's inequality says that the gradient of a function, of harmonic function, so if f is discrete holomorphic in a domain omega epsilon, then gradient of f is at most some absolute constant over distance to the boundary times maximum value of f. So this is well, this is true even for harmonic functions, so maybe I will just write harmonic. So this is sort of the key tool in complex analysis if you want to write estimates, because it says that if you have an analytic function or a harmonic function which is bounded, you have a bound on its derivative. And then its derivative is itself an analytic function, so you have bound on its derivative of derivative and so on and so on. So you can bound like first 10 derivatives, then it's in a very nice Sobolev space, so you can do all sorts of estimates. Now, the problem here is that up to now everything was easy because we didn't have we didn't have to multiply functions. So let's put a small remark. So why it already becomes difficult. So the small remark is that if f and g are holomorphic, then, well, that should have been a property. Then f plus g are also holomorphic. But it is not true that f times g is holomorphic. So the usual proof of Harnack's inequality, if you do it not with harmonic functions in arbitrary dimension, but in complex analysis context, is that you use some integral representation formula. So you use this formula that f of z is equal to 1 over 2 pi I integral of something something. And for example, this already requires writing things like f of z divided by z, which we cannot do because f of z divided by z is no longer holomorphic. 1 over z is not a holomorphic function. So this is a problem. So this is somehow the first theorem on this board where one has to do something where the usual proof in complex analysis cannot be directly transferred. But fortunately, this is also known for harmonic functions in n dimensions, so there are other proofs. Maybe I will leave it so far without proof, and we'll do it later. But this is sort of the major issue, that if f times g would have been holomorphic, then we would just transfer all the complex analysis. There would be no difference. But since it's not in general true, then we easily transfer everything where we only needed to add functions. But already the Cauchy formula 1 over 2 pi I integral of f of z over z minus zeta, it doesn't. We cannot prove it. It doesn't exist. So the ramification of this is that maybe I should, so that it's not an empty statement, I should make an example where two functions have product which is not holomorphic. So if I take function 1 on a square lattice, restricted square lattice, it is holomorphic. If I take function z and restrict it to square lattice, it's again holomorphic. It's very easy to check because the difference along vector AB is just b minus a. If I take function z squared, here it's again holomorphic because, well, one has to check. So for this, so z times z is holomorphic. So it's a wrong statement. There are two functions who are holomorphic whose product is also holomorphic. But if you look at z cubed, it is not a holomorphic function anymore. So one other ramification of this is that if you want to do some sort of Taylor expansions, then they start with 1 z squared. But then discrete analog of the cube is not the cube. It's some function which is the discrete analog of the cube would be a function which is primitive of z squared. And primitive of z squared is not exactly the cube. It's approximately it is, but not exactly, and so on. Okay, so maybe I do a few historical remarks. So essentially this on the square edge. So as I said, there was this paper about dissecting squares by Brooks, Smith, Stone, and Tate, but they never mentioned that they are actually working with the discrete holomorphic functions. And then I think the first paper where this really appeared was a paper by Jacqueline Ferrand, and that was in 1944. Well, essentially what she did, it was what is on this blackboard, but she couldn't prove Harnack's inequality, which she needed to pass to the limits, because her goal was to show that in certain cases you indeed converge to continuous holomorphic functions. So she had conditional statements of this sort, but she did not prove that statement. That statement was proved a year later by Verblunsky, and then she has a book about complex analysis and Dirichlet principle, which appeared some years later, where she shows that you can prove Riemann uniformization theorem using discrete functions. So it's well, then she had a book, so she married meanwhile. So the book is under name Lelong-Ferrand, and her husband was also a well-known multidimensional complex analyst. So in the book, So in the book, what she does, she shows. So maybe we'll do this a bit later. She proves. She does a proof of the Riemann uniformization theorem using preholomorphic functions. So she takes a domain. She defines some sort of discrete analog of holomorphic map to a disk. And then she passes to a limit and shows that it converges to a real holomorphic map to a disk. And then there was an American by the name Duffin who wrote lots of papers in 50s and 70s, and his students also did. So they did basically this theory on the square lattice. They used it to construct a few interesting objects like Bergman kernel, etc. But I wouldn't say that there were any theorems which weren't proved before by the usual complex analysis method. And then he also considered, proposed several generalizations of one which is maybe the which is pertinent to our case, is the considering discrete holomorphic functions on rhombic graphs where you tile by rhombi. So he observed that, I cannot draw a rhombic graph. So you tile, so square lattice is of course an example of a rhombic graph. So he considered first square lattice, and then he showed that most theorems you can generalize to a case like that. And the reason why we are not doing it for this case is first because it gets more messy. So here the definition is the same, that for any rhombus, the difference like that is equal to the difference like this. And for the rhombus, if you notice that the diagonals, they are orthogonal and intersected their centers. So for the rhombolytis, you still would have the same property that restrictions of discrete holomorphic functions, they are discrete holomorphic up to order 4, because you have here difference along two lines which intersected their center. But the problem with this lattice is that you cannot differentiate more than once. So here, if you define derivative, it will be defined at the centers of rhombi, and it's no longer a rhombic lattice itself, and you cannot differentiate one more time, and that makes big difference when you are writing estimates. Okay, and then more or less, I think it's up to recently, it's more or less it. So more recently there were papers by Kenyon and who did the relations of discrete analytic functions to dimers, and by Mercat, who did them for the Ising model. Then there were a few papers where they were applied in some sort of computer science or graph theory spirit. So, for example, there was a paper of Lattice, Lovesh, and Bigiamini, and Lovesh has an exposition where such applications are discussed. So it's, let's say, and then there is also a theory which is slightly different. So we were speaking about discrete, linear discretizations of Cauchy-Riemann equations. So there are also nonlinear discretizations where you can ask for some discrete conditions which are nonlinear. And this I won't discuss at all, but they were very interesting. And for example, if you take circle packing, and so suppose that you, well, whatever, you take a circle packing which has topology of hexagonal lattice, and you take the usual hexagonal lattice circle packing. So this sort of gives you a kind of a function which for every point on hexagonal lattice prescribes the coordinates of the corresponding point in this packing. So this would satisfy some local conditions which are nonlinear discretizations of Cauchy-Riemann. It's fairly easy to write them. You just write condition that you put circles and they are tangent, and the two circles are tangent means that the distance between their centers is equal to the sum of their radii, so which is a nonlinear condition. This led to very interesting mathematics, and this actually proved some theorems which weren't proved by the usual complex analysis. So Adet Schramm and they proved Kirby uniformization conjecture for some domains using this. So Riemann uniformization theorem states that you can map any simply connected domain on a disk. Kirby conjecture states that any domain with some holes can be mapped to a domain where all the holes are circular. So all the holes are points or disks. So Schramm and he proved this for domains with countably many boundary components using discrete circle packings, and it indirectly uses discrete Cauchy-Riemann relations which are nonlinear. But as this so far hasn't been applied to probability, so I won't really discuss this. And it's even a bit misleading because usually when we discuss planar maps, circle packings appear, but they appear in slightly different contexts. But it's related but slightly different. So it would be nice to do something here, and especially because in probability you can see nonlinear relations appearing. So if you open McCoy and Wu book on the Ising model, they have some nonlinear relations for spin correlations. And if you check closely, they are related to nonlinear complex analysis. But so far there was no connection, so we will restrict ourselves to the linear case. Okay. So now what remains, it remains to go 20 minutes. So what should I do? Yeah, okay. So let me maybe just describe how discrete homomorphic functions arise, for example, in the uniform spanning tree. So any questions? Should I go faster? No? Yes. Yes. Oh, well, what I mean is just that the derivative, partial derivative is bounded. So x derivative is bounded and y derivative is bounded. Okay, there are differences. Differences are bounded, yeah. So what I mean there is that the difference is bounded. Yeah, okay, the difference is well, you see here it's a bit imprecise because I said I have this point z, I have distance to omega. Okay, you can instead you can write here f of z minus f of z plus epsilon divided by epsilon is bounded by something. So you can write that, yeah. So it's let's say, f of z plus epsilon minus f of z divided by epsilon. And the same also holds in other direction, the I direction. So it's, well, there is, in a sense, the gradient of harmonic function is an analytic function in the sense of Kirchhoff. It's a flow on edges, yeah. So you can say that, yeah. Well, okay, canonical, again, you can propose a few more canonical definitions. It's the same as our definition of harmonic function corresponds to nearest neighbor random walk, to simple random walk. But you can choose any other random walk, and you have a reasonable definition of harmonic function. Okay, so let's just maybe see how they appear in the uniform spanning tree. So and tomorrow then we do the Ising model of. Okay, so example. So uniform spanning tree. Now I will do a Kirchhoff-style example. There are more interesting ways how they appear there in Kenyon's work, and that we'll do time permitting. So so let's maybe. And maybe even I'll do. So let's take some box. Yeah, actually, let's use uniform spanning tree to prove Riemann uniformization theorem. Yeah, that's exactly work for 15 minutes. So what we do. So since we want to uniformize, we want to map this discrete domain to something. Yeah, let me maybe make more interesting discrete domain than just a square. So something like that. Let's uniformize it, for example, to a rectangle. So if we want to uniformize it to a rectangle, we have to mark 4 points on the boundary. So let's mark 4 points here and here and here and here. And we want to run a uniform spanning tree, but we want these points to be distinguished. So what we do, we just wire 2 of the arcs. So we consider uniform spanning trees where this arc is wired and that arc is wired. So we consider a model which we'll call UST. So it's, well, if I denoted this by A, B, C, D, so on omega epsilon graph with wired arcs AB and CD. So we consider all the possible trees. So this is an example. Yeah, maybe I should have used colored chalk. So this is. This would be sort of an example of what we can get as a configuration. And these trees have to include this bottom line. So let me maybe make it in another color. And the top line. So if you look back to Kirchhoff, so he proves, because he mostly works not with the planar graphs, he proves that there are certain discrete harmonic functions, and these discrete harmonic functions, in this case, of course, they relate to discrete homomorphic. So we will maybe directly prove using discrete homomorphicity, and in our case, so there will be a function which has real part and imaginary part, and the imaginary part is better defined in terms of slightly different model. So let's say denote it to UST, And this is a forest of two trees, which you obtain if you cut connection between top and bottom here. So it's a forest which has two trees, one rooted on DC and one rooted on AB. So this is forest on omega epsilon, first tree on AB, second tree on CD. And now we define two different functions. So let's say function f1. So function f1 will be defined on the vertices of the dual lattice. So function f1 of z is the probability for the UST model that z is to the right of, and if we have a tree, there is a connection in this tree between top and bottom arc. So we look for the probability that z is to the right of this connection. So it's right of, let's say, gamma. So let me just draw another picture. So we have this tree, and in this tree there is a unique connection between top and bottom. Because it's a tree, it's a connected graph, so there is a unique path in this tree which connects top and bottom, starts on some point on the top, ends at some point on the bottom, and we ask for the probability that our point, z, is to the right of this connection, gamma. So this is defined for the points which are centers of plackets. And the other function which will be defined for the vertices of our lattice, so let's say vertex u, so f2 of u, it will be a probability in the other model that u belongs to the first tree. U belongs to the second tree. Second tree. So this is, in the second model, we have two trees. So there is tree which is growing from below, and there is tree which is growing from above. So this is the probability that our point u is on this second tree. And the other one is probability that point z is in this half. So are the definitions clear? What? Because it will converge to the real part. It is 0 here and 1 here. Yeah. Sorry, why don't? No, okay. Yeah, that doesn't really matter. It will be. You mean that I will have to do first tree there, not? No, I don't see. Okay, we'll check. It will either work or not work, and then we'll see. And so the theorem is that, so you see there are two functions, which one is defined on the blue lattice and another on the orange lattice. So it turns out that they are real and imaginary part of a holomorphic function. So on two dual lattices. So it's if you take this sort of skewed lattice and rotate by 45 degrees, so you have real part on blue vertices and imaginary part on orange vertices. So the theorem is that if you take f1 plus I f2, then it is holomorphic. But for f2, you have to normalize by a coefficient. So we have to put coefficient norm the number of double trees over number of trees. So we have to somehow normalize this to one probability measure. Sorry? So you say that minus will be here, yeah? Yeah, okay, let's no, a second. F1. No, I think this is a holomorphic. So Wendell seems to be thinking that there should be minus here. So this function is either holomorphic or anti-holomorphic, and we will see, we will discover this in a second. Yeah, that's the question, yeah? No. Yeah, okay. So no, but wait a second. It's equal to 1 here and 0 here. And the real part changes 0 to 1. Well, no, I'm confused. Well, so okay, let's do the proof, and then we'll see. So so let's do the proof. So we have to check Cauchy-Riemann equation around some placket, and to do so, well, we just have to compute some probabilities. Okay. So this is the big part of our graph, and one of the function is defined on such vertices, another function is defined on these vertices, and let's denote this by u and v, and this we denote by, let's say, z and w. And what we want to check that I times f of v minus f of u, f of v minus f of u is I times f of w minus f of z. Now, f of v and f of u, there, for u and v, we just have the function f2. So there is I in front of it. So it's I f2 of v minus f2 of u. And here it's I f1 of w minus f1 of z. So they can go away. So we have to compare the difference of f2 functions with the difference of f1 functions. Now, what is the difference of f1 function between these two vertices? Well, we have to compute the difference of probabilities that these 2 points are right of the curve gamma. So this is the so the 2 functions f1 are probability that w is right of gamma minus probability that z is right of gamma. And if we take uniform spanning tree configurations, there are configurations where they are both to the left or both to the right. So this we can cancel out. So essentially, we can rewrite this as a probability that y is right of to the right and z is to the left of gamma, minus probability that w is left and z is right. So is it clear? So we are already doing much better because if those are events of probability comparable to whatever 1, then these are much small probability events. And what is included in this event? Well, it's the probability when w is to the right of the curve gamma and z is to the left, so the curve gamma is forced to pass in between. When going top to bottom, it is forced to pass in between. So we have configuration which is something like one drawn here, that when the curve gamma goes from top to the bottom, then it passes through this edge. And the other function here is a similar probability, only when it goes from bottom to the top. So the other function would imply that it goes like this. So maybe I would draw two small pictures here. So this would be a picture like that. And this would be a picture when it passes, but with a twist. So this is a picture when the point w is on the right and z is on the left. And this is the picture when it is vice versa. Are we okay? So those are small probability events because we already passed through this edge. So Kirchhoff, actually, what Kirchhoff was doing, he was proving that such probability is harmonic. And this holds on any graph in any dimension. So we will use tricks here. So we will just show that it has harmonic conjugate. So this proof only works for this dimension. Now, what does it mean that it passed through this edge from z to w? Well, it means that if we erase this edge, we split our tree in two parts, where one part contains upper arc and the other part contains the bottom arc. If we erase arbitrary edge, we're not guaranteed to split our tree. We always split our tree in two parts, but we're not guaranteed that up and bottom are in different components. But if we erase one edge on this path, then the up and bottom are in different components. So we erase it, up and bottom are in different components. So what we can rewrite this as probabilities of two similar configurations. And one configuration, it contains point v in upper tree and point u in lower tree, and the other vice versa. So we have rewritten this as a probability that v belongs to the first tree and u belongs to the second tree, minus probability that v belongs to the second tree and u belongs to the first tree. And since here the probabilities were for the UST model, when we change it here to the model with two USTs, we have to change the way we were counting. So we have to put the coefficient which relates the total number of trees in the model. And this is exactly what we have there. Okay? So now the conclusion. So if I go over time now, do I get to stop early on Saturday? So how long over time can I? Should I stop? I can just stop, or yeah, maybe I finish this. It will take like 5-10 minutes. So so the conclusion is that our function f, so f which is f1 plus some constant, this number of trees over number of trees. So the conclusion was that this function is homomorphic. Now, what about the boundary data for this function? So what can we say? I already put this constant in the definition of f. Yeah, well then. Okay, so this function is homomorphic. Now, what can we say about its boundary values? So about function f2, we can say that top part belongs to the top tree, and bottom part belongs to the bottom tree. And about function f1, we can say that the right arc is to the right of z, and the left arc is to the left of z. So what we can say that here f1 is equal to 0, here f1 is equal to 1, here f2 is equal to 0, and here f2 is equal to this normalizing constant. So if we would be dealing just with one function, say f1, which is harmonic, it would mean that it has Dirichlet boundary values here. But on these two arcs, it has Dirichlet boundary values for the harmonic conjugate, meaning Neumann boundary values. So in terms of f1, it's Dirichlet-Neumann boundary value problem. In terms of analytic functions, it's just for every arc, it's Dirichlet either for real part or for imaginary part. Now, what can we say? Well, we can say that, f1 is harmonic. f1 has absolute value at most 1, because it is between 1 and 0, and by maximum principle, it is at most 1. So it means that if we apply Harnack's inequality, we have bounds on its gradient. So it's we have control over gradient of f1. But gradient of f1 is equal to gradient of f2, because the difference of f1 and difference of f2 are the same. So we have control over gradient of f2, which a priori we don't have, because f2 is defined as some probability between 0 and 1 times some normalizing constant, which we don't know. It might be, as far as I know, it might be like 1 million and tending to infinity if mesh goes to 0. So this, by the way, immediately sort of means that this constant stays bounded when we take smaller and smaller mesh. So we have this sort of control, which implies that there is a precompactness. So when we change epsilon, our functions still have uniformly bounded Sobolev norms, etc. So they have they lie in a finite ball in some nice space. So we can choose converging subsequence as mesh goes to 0. So as mesh goes to 0, we can choose a subsequence of our functions which converges to something. And then we already know that the limit will be analytic. So we know that, sorry to step on your ears. So we know that f, okay, so f epsilon converges to some f, which is continuous. So again, it's sort of, by convergence, I mean that f epsilon is a function defined on a lattice. So we continue to say linearly in between, or constantly in between. So for every placket, we just make it equal to its upper right corner. And since we have Harnack's inequality, we know that it doesn't make of very much oscillation because our function has good bounds for the gradient. So this function uniformly inside converges to some function f, and function f is holomorphic because we had this property that limit of holomorphic functions is holomorphic. And f satisfies the same boundary value problem. So the problem was, I want to remind that the real part is equal to 0, real part is equal to 1, imaginary part is equal to 0, imaginary part is equal to a constant, which is limit of this ratio. So what does it mean? So how can we make such a function? Well, what I claim that then the function f is just a map to a rectangle of width 1 and height c. Why? Because we have a function which has boundary values as there. So we know that this arc by this function is mapped in a vertical axis. This here it's imaginary part 0. It's mapped into this axis. This arc is mapped into line parallel to imaginary axis, and this arc is mapped into line which is parallel to horizontal axis. Now let's try to do argument principle. Let's try to ask how many times this value is taken by our function. So what happens when we go around the boundary of our domain? When we start, we go somewhere on this line. Then we switch to going on this line. Then we switch to going on this line. Then we go on this line, maybe back and forth, and we arrive at the same point. How many times can we walk around this point here? Exactly once. It's just topologically not possible to go less or more because no matter how much we wiggle on this line, it has exactly the same effect as if we just traversed this interval in terms of circumnavigating that point. So it's walking on this line, then on that line, then on top line, then on left line. It's the same effect as just walking around the rectangle. We walk around this point once. So all the values inside are taken exactly once. All the values outside are never taken because we don't walk around them. So the argument principle implies that f is a conformal map from omega to this rectangle. And now, how do we determine the height of the rectangle? Well, so Riemann uniformization theorem states that any domain can be mapped to a disk, and there are 3 more parameters to play with. So if I had 3 points, I could send them wherever I wish. But the 4th point is a conformal invariant. And usually people write it by saying that if you have domain with 4 marked boundary points, there is exactly unique rectangle to which you can map it up to homothety. So C is the conformal modulus of these points. So what we accomplished, we proved Riemann uniformization theorem, only well we uniformized to rectangle, but it doesn't really matter. It's an easy exercise to write a map of rectangle to a disk. And we also proved that the conformal modulus of 4 points can be expressed in terms of uniform spanning trees. That the ratio of the number of these double trees and the number of trees, it converges to conformal modulus of this domain. So conformal invariance can be extracted from the uniform spanning trees. Yeah, I think I'll finish here. Questions? I'm a bit intimidated by this group here. So questions? No, it just stops at your limits. So questions? Remarks? Yes? It's well, it's because so if your boundary data are smooth, then you can you can work without it. You can just write, then you don't need it. But if it's non-smooth, imagine that your boundary data is something of a sort. So you have, say, a disk, and the boundary data is that the function is very, very small, and then it has a spike on the boundary. So when you solve the Dirichlet problem, it will also replicate this spike inside. So when you approach this spike, your gradient will grow. So a priori, so what Harnack's principle says that no matter how wiggly are your boundary values, well, inside the domain, the gradient is smooth. But when you approach the boundary, you might have to address such questions, and then, of course, the gradient is not necessarily bounded. So it says that, like, say, in a smooth domain, it can explode like 1 over z near the boundary. And this indeed happens if you draw pictures of this kind. So it's almost sharp. Question? Yeah? Can you speak a bit louder, please? Well, yeah, that's, well, I mean, I use current Friedrich-Levy theorem from yesterday. So they say that for the Dirichlet problem, the boundary values converge okay. And for two arcs, those are Dirichlet problems for F1. For two other arcs, it's Dirichlet problem for F2. Now, of course, one has to work. So one can either use their paper. Well, one has to work, either read their paper, reproduce the proof yourself. So what they do is that, well, you have to get an estimate which you can integrate up to the boundary. So it's so you have to show that somehow, well, your function converges inside the domain. But theoretically, you might imagine that it converges inside, but near the boundary it sort of flaps and goes haywire and diverges. So you have to show that you know here, and as yesterday, you know the energy norm inside the domain is bounded. You know that integral of gradient of f squared is bounded by some absolute constant. So you have to show that near the boundary, this doesn't allow for much of a wiggle. If the domain is smooth, that's the case. It doesn't allow. If domain has cusps, no, then you are in trouble. Then a priori it might wiggle. But for smooth domains, it allows enough control. Yeah, maybe we'll do this estimate later. But indeed, you're right. You have to work. It's when you approach boundary, a priori, it's a subtle question. Yeah. Sorry? Oh, yeah, sure. But so what I'm saying that this proof might be more difficult. But also, you can approximate any domain by smooth domains. Yes, yeah, sure. There is one thing, what Wendelin pointing out is that you can use probability definition of F1 to get some estimates. So there are two possibilities if you run this probabilistic argument also for the Ising model. One, you prove that function is holomorphic, satisfies some boundary values, and a priori, a priori this thing determines uniquely the function, the thing that it is holomorphic and has these boundary values. So a priori, all the estimates you can obtain from these two facts. But in principle, you are also allowed to use the estimates which come from probability. You can very well say that with some algorithm, you can very well estimate probabilities that random walk does certain things, and this will give you estimates for F. So this can be used to obtain the proof for any domain. So it's, but yeah. Where did I use the fact that the domain is simply connected? Well, I mean, in argument principle. Because if there is a hole in my domain, then to apply argument principle, what I need to do, I need to count how many times my boundary winds around the value. So now, if there is a hole, I have to traverse this boundary, and then I have to traverse this boundary. So for this boundary, I have to figure out first what are the boundary values. And it's a good question. I think in this case, probably I don't know. Probably I don't know. well, it slightly depends how you define your domain. I don't think you would easily be able to easily tell what are the boundary values for this case. So for easing, for example, there are certain observables where you get some boundary values on interior components, like saying that it's a Neumann boundary value problem, which allows you to uniformize domains too. But say, for example, for percolation observable, for this observable, I don't know what are the boundary values. So the observable which we'll be discussing in easing, it can allow you to uniformize any domain with a number of holes. So in principle, yes. Yeah, I think Dima is actually right that it's a Neumann boundary condition that 2 points on the boundary, they are never separated by a vertical slit, meaning that this function is constant on the boundary. So meaning that this function, the f1 function, is constant on this thing, meaning that it maps to a vertical slit. Yeah, I think the problem is so this thing, it cannot be this vertical slit, it cannot come through a hole. It always have to go on the left or on the right. So all points on the hole, they are either to the left or to the right. So function f1 is constant on this component. So what do we arrive at? We arrive at this thing being mapped to some vertical slit. And if there are two things like that, then they are mapped to several vertical slits. And now the question is, what exactly will be the ratio of the sides and what exactly are the positions of these slits? And this is given by conformal modulus of this guy. So the conformal modulus of every hole adds 2 numbers to conformal modulus, which is, for example, in an annulus, there is, for example, if you put a circular hole, it's, maybe, 3 numbers. Yeah, 3 numbers. It's coordinates of the hole and the radius of the hole. So here, each hole has 3 numbers, coordinates of the lower end and the length. So there are 3 times 3, 9 numbers, plus there is a ratio of size. So there are 10 parameters. And for every picture like that, there is a unique picture of this sort. And apparently, you can uniformize with the uniform spanning tree. Yeah, OK, so we actually proved that any domain with finite number of holes using uniform spanning tree can be uniformized by a rectangle with vertical slits. You can also do horizontal slits if you rotate. And the cubic conjecture I mentioned, it says that you can draw, instead of slits, you can draw round holes. And that's not settled. So this is settled for any number of, there is an analytic proof which uses no probability whatsoever, which maps any domain with any uncountable number of holes to a domain with only vertical slits. So it's a theorem of Schiffer. And but for round holes, we don't know. It used to be a big open problem, but I think now people have given up. But the best result belongs to He and Schramm. Questions? Yes? No, that's well, algebra. Yeah. Well, the problem is why. Well, okay. So the problem with that there is no discrete complex field. So you cannot. You can take these Gaussian integers z plus iz. You can multiply them, but you cannot divide. So since it's an algebra, but not a field, this is why this whole thing is problematic. Now, if you want to define algebra of homomorphic functions, yes, of course you can, because it's as I mentioned, you can take basis not of 1, z squared, z cubed, etc. You can take a basis where each next function is primitive of the previous one. This will be analogs of polynomials, and you can define the product by saying that the product of z to the power k analog and z to the power l analog is analog of z k plus l. So it will give you a sort of multiplication of prehomomorphic functions, but it's not pointwise multiplication. Actually, it's non-local. So it's sort of not so bad. I mean, to know to good precision product of your functions near this point, you only need to know values in the immediate neighborhood. But all the values count. So all the values count, but main part is played. So it's almost local, but it's not local. So you can, but it's not a local multiplication. Yes. Good. We just worked it out, I think. No, I didn't know it works for the scrolls. Yeah. No, I don't think so. So there is this book by Lalonde-Ferrand where she uniformizes. I don't remember. She either uniformizes to triangle or to rectangle or to half. I don't remember to which one she uniformizes. It's very nice, but it's a forgotten book. It's like from 1950, and there is this chapter. It's a book mostly about Dirichlet class of conformal maps, and then out of the blue, in the middle of the book, there is a chapter about this for no apparent reason. But otherwise, I don't think it's written up. Yeah, so it's so certainly not through the uniform spanning tree. Yeah, but I'm not going to write it up even if you give me a discount on Saturday. Yeah. Questions? Well, thank you. Sorry for running